Today we'll be dealing with logarithms, which is our week 1 topic for SS2. Our week 1 topic for SS2. Before we proceed, let's do a quick revision on standard form. Now, what's standard form actually? Standard form is a number, normally you have a number represented. For example, you have 8,300, 120,000. You have numbers like this represented normally like this in digits, but when it's represented in the form of m times 10 raised to power n, that is with when you multiply a number between 1 to 10 by 10 raised to a particular power, when it's represented in that particular form, we call it a standard form. Now, if we are to represent this in standard form, how do we represent it? So very quickly, we have 8,300, right? Now, to represent this in standard form, it means whatever we'll be writing here as m, or in the form of m now, would be a number between 1 and 10. So how do we do this? We actually do what? First of all, count the power of 10 you have here. Start from here. You count 0, 1, 2, 3. So definitely it is times 10 raised to power what? 3. So how do we now represent it now? You take this first digit, and then if there's any other digit beside it, not after it, you put it after as a decimal point, or after a decimal point. 8.3 times 10 raised to power 3. This is quite easy. What do we do again? Start counting from here. Just count 0, 1, 2, 3. Then you write times 10 raised to power 3. Then count 8. Or you write 8.3 times 10 raised to power 3. If you have say 52013400. Of course, we can't represent all this in standard form. So what do we do? Sometimes we take the first 2 digits, sometimes we take the first 3 digits. And what do? We start counting from here again, like I taught you here. What do we do? 0, 1, 2, 3, 4, 5, 6, 7. So you write times 10 raised to power what? 7. Then what do we write? 5.2 times 10 raised to power 7. This is how we represent this in standard form. So we actually estimate this. We don't put these remaining values. Now, also, for example, you have 30,000,000,000. How do we write this in standard form? We are dealing with positive standard form. We will soon go to negative standard form now. Now, how do we write this in standard form? You start counting 0, 1, 2, 3, 4, 5, 6, 7, 8. So you have what? Times 10 raised to power 8. You have what? 3. You can write 3.0 because the digit after it is what? Actually 0. Are you getting me now? So you have 3.0 times 10 raised to power what? 8. So what if you have a number like 5? We have a number like 5. How do you represent this in standard form? Actually, it's represented as what? When you start counting from here now, what do you have? Only 0. So you have times 10 raised to power 0. So you have 5 times 10 raised to power 0, or 5.0 times 10 raised to power 0. What of probably 322? How do you represent this in standard form? 0, 1, 2. So you write first times 10 raised to power what? 2. Quite easy. Now, you now write what? 3.2. You can leave it as this, or you can write 3.22 times 10 raised to power 2. It's all the same thing. Moving towards negative power, which are actually decimals. So, for example, you have 0.1. This actually gives us 1.0 times 10 raised to power minus 1. How do we get this? How many zeros do we have before the first significant figure? You should know what significant figure means now. Any digit greater than 0. How many zeros do we have before the first significant figure? That's how we get the negative power to put here. So, for example, you have 0.0000012. Because after your decimals, you don't call them like whole numbers again. You don't call this 0 0 0 0 12. No, you call it 0 0 0 0 1 2. You call each digit one by one. And so having this, we actually just simply do what? Count 1 2 3 4 5 times 10 raised to power minus 5. That's 1.2 times 10 raised to power minus 5. So if you have 0.0030000429, how do you represent this? It's still quite simple. This 0 after doesn't really matter. What is important is this 0 before the first significant figure. Do take notes. And so we have times 10 raised to power minus what now? 1 2 3 minus 3, right? What do we write here? 3.0 times 10 raised to power minus 3. Okay, we have another number like this, 0.00000090934. We don't approximate anything here. What do? We just count. We write times 10 raised to power minus what? 1 2 3 4 5 6 7 minus 7. Now, what's the digits? What's the first significant figure here? 9. You can actually write 9.09 like this. And this is how we represent our decimals in standard form, talking about our negative powers of 10. Moving forward into logarithms proper. Now, there are some basics I would not be bothering us with, because I'm working, like I said, I'm working with what? SS2 scheme of work. Now, if you are having challenges as touching logarithms, do well to watch our SS1 second week topic, which is actually logarithms. There, I'll be dealing with logarithm at its basics. So I'm working with the scheme of work. I'm working with your scheme of work. Looking at logarithms proper, we have the logarithm of a number to be something like, it always looks like, where this is the what? Characteristic, and this is known as what? Mantissa. Okay, so this is the characteristic and this is the mantissa. And you know that naturally log is always what? With a base of what? 10. So if you have something like log 1000, this is actually equals to 3. Now this brings us to the relationship between indices and logarithms. So what relationship does indices have with logarithms? Now, if log this is equals to this, like I said earlier, all logarithms that do not have any base indicated are naturally in what? Base 10. Except you have the base indicated. For example, when you have something like log 2 4. Now, you have this, it is indicated that the base is what? 2 to the power of what? 4. Now, when you have this actually means that what? Like I said, it is base 10. This actually means that what? 10 raised to power 3 is 1000. Now, this is the relationship between indices and logarithm. I will take another example. Look at the one I just wrote here. Log 2 power 4. Now, log 2 power 4 is actually equals to what? To 2. It's actually equals to 2. Now, how do we connect this with indices? 2 raised to power 2 is actually 4. This is the relationship between indices and logarithms. Do take note. Moving very quickly with the laws of logarithm. Now, we have log A plus log B as long as they have the same base. If they don't have the same base, this law does not apply. As long as they have the same base, what will happen is that the powers here will be multiplied together. Now, if this log is subtracted from this log, as long as they have the same base also, it will be they will be represented with one log and that same base, and then the powers will be what? Divided. That is, B will be dividing A. Now, if it was log B minus log A, it will be what? Log B over A. Take note. For example, If you have log 25 minus log 15, what does this give us? What does this give us? This will actually give us what? As long as they have the same base, like I said, it will give us log what? 25 over 15, which is actually log what? Log 5 here is 3, 5 here is 5. Log 5 over 3, it's a base of 10. Now, if, for example, you are given a question to solve, because you will see questions on logarithms like this. Say 5 or 59.40 times 3.19 divided by 42.22. Now, they say, or if they ask you your question, to solve using what? Logarithm what? Tables. How do we solve this? Actually, log this, take note, log this is actually equals to log 59.40 plus log 3.19 minus log 42.22. If you take this law and read it backwards, this is actually what you're going to get. So when you get the what you do actually is that you get the log of this one, find the log of this one, and find the log of this one. What do you do with that log? When you find the log of this one, you, let's call it A now, you add it to the log of this one, B. Why? Because look at it here. Whenever you're multiplying these numbers like this, you can always put the log as what? You can always add up the log of the both numbers instead of multiplying it directly. You can just find the log of both of them and add it up together, applying this law of logarithm. Now, this one will now be what? Minus here. When you have found the logarithm of 42.22, let's call this C. This is how we get the solution for questions like this. Remember, it's when you are asked to solve using logarithm tables that you go through this path. Okay, we will be finding now the logarithm of the following values. We have 59.40, 3.19, 42.22, 40.00, 56.3. How do we find the logarithm of the following values? Now, what you do first is that you check the highest value here, the highest digit. What place value is it? From the place value, we can now deduce the power of 10 that it is in. Now, this is what? This is 10 to the power of 1, right? So, instead of writing 10 to the power of 1, we just write 1 as a whole number. Remember that I told you that your logarithm, for example, looks like 1.3249. This is the integer, right? And this is the decimal. This integer is known as your characteristic, while your decimal is known as the what? Mantissa. Okay. 1 plus whatever value we'll be getting now. How do we get the value now? 59.40. 59.40. If you look at our logarithm table here, look at this place labeled X, the column under this place labeled X. You will discover that what? You have from 10 to 54 here, then from 55 to 99 here. How does it work? We also have 0 to 9 here, and we have what you call differences here, 1 to 9 also. Okay, how does it work? For this 59.40 now, this is how we look for it. We look for 59 under 4 with a difference of what? 0. When you say a difference of 0, obviously there is no difference. Okay, now look at this now. we have 59 under 4. From here we have 0 to 54, right? This is 59 here. This is 59 under 0. So it means if you trace 59 like this, under 4 we'll be having this. We'll be having this. Now with a difference of 0, it means there's no difference. What actually happens is that you add the difference to the last digits. These are the differences here. For example, if it was under difference 9, you would have added 7 to this 8 here, being the last digit in this decimal. What is actually here is decimal. So you now have 1 plus what? 0.7738. Now, with a difference of what? 0, right? So there's no need to add up any difference again. You will now be having what? 1.7738. Very quickly, go to 31.9. Going to 31.9, you would have this. 3.19, is what? First of all, it has a what? A power of what here? 0, abi? That is power of 10 here will be what? 0. So it's 0 plus whatever we are getting here now is what? 31. Look at it now. Once we are done with this power, we forget about this decimal point here. We just go 31 under 9. Now there's no value at the back, so it's also a difference of what? 0. Okay, so 31 under 9 would give us what? 31 under 9. We have our 31 here. This is 31 under 0. If we trace it straight down, 31 under 9 will give us 0.5038. Now with a difference of 0, there's nothing to add to the last digit here. So we write the same 0.5038, which is actually what? 0.5038 in total. So that's the log of 3.19. Going quickly to the log of 42.22. The logarithm of 42.22. How do we do that? First off, we find what? The power of 10 here, the highest power of 10 here, which is what? We have 0, we have what? 1. So you write 1 plus. Now for this, we are now having what? 42. 42 under 2 with a difference of what? 2. So take note. 42 under 2 with a difference of 2. Like I said, once you have put this power of 10 here, you forget about the decimal point and just read it straight. 42 under 2 with a difference of 2. So you have 42 to be here. This is 42 under 0. So we put 42 under 2 is actually what? 0.6253. 0.6253. Look at it clearly here. Under 42 under 2, 0.6253. Now, with a difference of what? With a difference of 2, right? 42 under 2 with a difference of 2. So let's go. 42 under 2 with a difference of what? 2. So we trace it here and we have our difference of 2 to be also what? 2. Add that 2 here. It gives us 0.6255. Now take this and add it to what you have here. You have 0.6255, which is actually what? 1.6255. Moving very quickly to log 40.00. This is quite easy. What do we do? First off, the highest power of 10, which is what? 1. You have 0, 1. Remember the way I taught you. 0, 1. So you have 1 plus. For this one, we now have 40 under 0 with a difference of what? 0. And I told you that if it's having a difference of 0, there's nothing to add up here. So what do we do straight up? We just have what? Log 40 under 0. The difference is 0. We are not adding anything up. We just write it straight up. Now, log 40 under 0 is what? 0.6021. Take note, this might look like 6021. It's actually 0.6021. Don't forget to put 0.6021. Don't take it as what? As a thousand. So it is 0.6021, which is now 1.6021. So now we are solving, finding the log of a question in that has the highest value of what? Or highest place value of hundreds, which is 956.3. 956.3. How do we go about this? The highest power of 10 here is 0, 1, 2. So instead of writing 1 or 0, we write what? 2 plus. How do we get this? Now we have 95 under 6 with a difference of 3. 95 under 6 with a difference of 3. Now we look for 95 here. 95 is actually here. 95 under 6 gives us what? This is 95 under 0, under 1, 2, 3, 4, 5, 6. 0.9805. 0.9805 with a difference of what again? With a difference of 3. So we check 95 under 6 with a difference of what? 3. 1, 2, 3. A difference of 3 gives us a value of what? 1. So you add 1, like I said, to the last digits. So you have 0.9806. Now you have 2 plus 0.9806 actually gives us what? 2.9806. And this is how we find the logarithm of values. This is how we find the logarithm of numbers. Now, having gotten the logarithm values of these numbers, I've told us before, whenever you are multiplying the numbers together, when you find the logarithm values, you add it up. And whenever you are dividing an ordinary by an ordinary number here, you do what? You subtract its logarithm value. You subtract its logarithm value. Now we have this logarithm value and this one. Because they are multiplying the ordinary number here, what do we do on this side? We add it up. Now if you are adding this up, you would have 1.7738 plus what? 0.5038. 8 plus 8 gives us 16. Carry 1, right? 3 plus 3 plus 1, 7. 7 plus 0, 7. 7 plus 5, 12. So we write 2, we carry 1. This will give us what? 2.2776. Now we write this here. 2776. Actually, if you find the anti-log value of this is what you will be getting. If you find the anti-log value of this is what you will be getting. 189.486. And then what do we do to this? We subtract this now from this. And so we'll be having minus what? Minus 1.6255. 6 minus 5, 1. 7 minus 5 gives us 2. This gives us 5. This cannot go, so we do what? We take 1 from here. 12 in 6 is what? 12 minus 6 is 6. 1 minus 1 gives us 0. Now this is our final answer in logarithm value. How do we get the ordinary values? Or how do we get the ordinary number, the value in ordinary number form? You can either, or better still, you do what? You find the anti-logarithm. Better still, you do what? You find the anti-logarithm of this value. The anti-logarithm of this value gives us this. Now, we'll be going straight to how to find the anti-logarithm values of our log of numbers.